Let me remind you guys about where we are in talking about angular momentum. All right, so you remember that we have this concept of angular momentum as the cross product of position and regular linear momentum, right? It's the same as in classical mechanics. And so if we do that as quantum mechanical operators, this leads us to define operators of Lx, Ly, and Lz, and also the operator L squared, which is Lx squared plus Ly squared plus Lz squared. Right? And then what? Then we can find the commutators of these things. And so that was part of what we worked on yesterday. Okay, and so you could find the commutators of Lx and Ly, and that makes IH bar Lz. And likewise, Ly Lz commutator is IH bar Lx, and the Lz Lx commutator is IH bar Ly. Okay, so those operators don't commute. They are incompatible operators in that sense. Okay? And then we also figured out that the commutator of L squared with any of the individual components is equal to 0. Those things do commute. Okay, so this is summarizing the properties of angular momentum, we might say algebraically. That is, in terms of the algebraic relationships of the operators. So we're taking the information about angular momentum and we're putting it all in terms of these commutators. Okay? And then based on these commutators, we can decide, let's find eigenvalues and eigenvectors. Okay, so we want to find the eigenvalues and eigenvectors or eigenstates of L squared, and we can choose one of the components, but we can only choose one out of 3. We can't get all 3 of them simultaneously. And so what everybody chooses is Lz. Okay, so we want to find the eigenvalues and eigenvectors of those things. Okay, so that means the equations that we want to solve are like this. All right, we want to solve that L squared acting on some function is an eigenvalue times that function. And Lz acting on the same function is a different eigenvalue times that function. Okay, so this is what we're setting out to do. Okay, and so we want to find all the functions, and we want to find both kinds of eigenvalues, the Lz eigenvalues and the L squared eigenvalues. So as our trick for doing that, we use ladder operators. So we use ladder operators, which are the L plus and minus, the L, that is Lx plus or minus I Ly. Okay, and then we could see that the ladder operators move us up or down on some ladder. Okay, so let's see, here's the nice figure from the textbook. Okay, so here's their the ladder of states. Okay, so you imagine that we start with one state, this F. Okay, and it has an LZ eigenvalue which is mu. And it also has an L squared eigenvalue, which is lambda. That's not written right here. Okay. And so then we can hit this state with an L plus operator. We get that state. Okay. And then the LZ eigenvalue is mu plus h bar. The L squared eigenvalue is still lambda. It doesn't change. Right. If we hit it with L plus again, we get now even higher. LZ eigenvalue is now mu plus 2h bar. The L squared eigenvalue is still lambda. Okay, and so we can keep going up by hitting with L plus over and over. And likewise, we can hit with L minus over and over. And the LZ eigenvalue changes to mu minus h bar. Do it again, mu minus 2h bar. Do it again, mu minus 3h bar, etc. Right? And so this keeps going until we get to the top or the bottom. Okay? And eventually we have to reach the top of the ladder up here. Here's the top. It's F sub t for top. Okay. And this is the top, meaning that the LZ eigenvalue can't go any higher. Likewise, if we keep going down, we get some negative eigenvalue, and then it can't get any more negative. So this is the bottom of the ladder. Okay, so what do we know about the top, right? That was what I ended with the last time. Okay, well, on the top, we have that LZ acting on F top is equal to mu top F top. And L squared acting on F top, well, it's lambda F top because every state on this ladder has the L squared eigenvalue equal to lambda. And we know that L plus acting on F top has to be 0 because that's what it means to be on the top, right? If you hit the top with L plus, you get 0. Right? And likewise on the bottom. Right? So on the bottom, we have LZ acting on F bottom is mu bottom F bottom. And L squared acting on F bottom is lambda F bottom because every state here has eigenvalue lambda. And L minus acting on F bottom is 0. Okay, So now let's do some tricks with operators to solve these things simultaneously. Okay, so whoops, that comes later. A good trick with operators would be to express L squared in terms of LZ and L plus and L minus, right? And so, we already have it expressed in terms of LZ and LX and LY, but instead of LX and LY, let's use L plus and L minus. Okay, so if we do L plus acting on L minus, okay, so that's LX plus I LY acting on LX minus I LY. Let's see, this is, what is it? It's LX squared plus I LY LX, right, from the second term times the first. And then there's this times that, so that is minus I LX LY. And then for the last term, it's plus I times negative I, so that's a plus LY squared. Okay, so this is LX squared plus LY squared plus I times the commutator of LY and LX. And this commutator is minus I LZ, times H bar. So overall, all of this stuff is LX squared plus LY squared plus H bar LZ. Okay, and so what do we have? Well, in this LX squared plus LY squared, for sure, that is L squared minus LZ squared, right, plus H bar LZ. Okay, so this gives us, now we can take this equation and put L squared on one side. Okay, and so we could get that L squared is equal to L plus L minus plus LZ squared minus H bar LZ. Okay, so this is one nice way of expressing L squared in terms of LZ, L plus, and L minus. Right? There is also a second way. If we had put the L plus and the L minus in the opposite sequence, the same argument gives us L squared is L minus L plus plus LZ squared plus H bar LZ. So this is a second way of expressing L squared in terms of LZ, L plus, and L minus. Okay, so now we're in a good position to see what happens if we put this whole thing applied to L top. Okay, so if we have L squared acting on F top. This gives us what? Well, let's use the second of these two relations. Let's use this one. Okay, so that is, oops, L minus L plus LZ squared plus H bar LZ acting on F top. Okay, so we multiply or distribute all this out. Okay, so L minus L plus acting on F top plus LZ squared acting on F top plus H bar LZ acting on F top. What is this? Okay, well, here we know this term is 0, right? Because this term, we take L plus acting on F top, that's 0. It's on the top. And then L minus acting on 0 is still 0. So that term is 0. What about the other terms, right? Well, LZ acting on F top once gives a factor of mu top. LZ acting on F top twice gives 2 factors of mu top. So that's mu top squared times F top. And then likewise, this is plus H bar mu top times F top. Okay, so this whole thing is mu top times mu top plus H bar times F top. But all of this is supposed to be equal to lambda times F top. Okay, so therefore, lambda is equal to mu top times mu top plus H bar. Okay, so that gives us some relationship between the eigenvalues. Okay, this good for everybody so far? All right. Now, let's do the same thing on the bottom. Okay. So if we have L squared acting on F bottom, now I'll use the other equation for L squared. Say this is L plus L minus plus LZ squared minus H bar LZ F bottom. Okay, and now if we expand all of this, okay, the first term has an L minus acting on F bottom. That's 0. The second term has an LZ squared acting on F bottom. So that makes a mu bottom squared times F bottom. And the last term is minus H bar LZ acting on F bottom. So that's minus H bar mu bottom times F bottom. So mu bottom times mu bottom minus h bar times f bottom. But again, this is all supposed to be equal to lambda times f bottom. Okay, so this gives us another equation relating lambda, but where am I going to write it? I'll write it over here, I guess. Lambda equals mu bottom times mu bottom minus h bar. Okay, so this is two relationships among the eigenvalues. Okay, so now let's combine these two equations, this and this, to get an equation that just relates mu top and mu bottom, okay, without any lambda. Okay, so that means, mu top times mu top plus h bar equals mu bottom times mu bottom minus h bar. Okay. We can use this equation to solve for one of the mu's in terms of the other mu. Suppose we want to solve for mu bottom. Okay, this is a plain old quadratic equation in mu bottom. Okay, this is the easiest bit of algebra in the whole semester, right? Because you can just solve it with the plain old quadratic formula like you learned in high school, right? And so let's do that, okay? So if we just want to expand all this to make something we can solve with the quadratic formula, okay? So on the right side, okay, this is mu bottom squared minus h bar mu bottom minus mu top times mu top squared minus h bar mu top equals 0. Okay, this is, say minus this. Okay, this is a quadratic equation. Okay, so let's solve it with the quadratic formula. Mu bottom is equal to negative b, so that's h bar, okay, plus or minus the square root of b squared, that's h bar squared, minus 4 times 1 times c, so plus mu top squared plus h bar mu top. Okay, all divided by 2. Okay, can I simplify this? Okay, this is h 1/2 h bar plus or minus the square root. Here, let's see, 4 mu top squared plus 4 h bar mu top plus h bar squared. Okay. So if I haven't made a mistake, this is solvable. Or, I mean, it's solved, it's simplifiable. Let's see, this thing inside the square root, this should be 2 mu top plus h bar squared. Is that right? Yes, it's right. Okay, cool. Okay, so this is 1/2 of h bar plus or minus 2 mu top plus h bar. Okay, so there are two solutions depending on whether I choose the plus or the minus. Okay, so if I choose the plus, this is 1/2 of 2 mu top plus 2 h bar. That's all. Okay. Or it is 1/2 of, if I choose the minus, then the h bars cancel, and we get just -2 mu top. Okay, so that means, here, I better write the final answer on the next page. Okay, so mu bottom is either equal to mu top plus h bar or negative mu top. Okay, so if we look at these two solutions, we could say, well, there's something wrong with the first one, right? This is wrong because the bottom can't be above the top. Right? The bottom is supposed to be a low negative eigenvalue. The top is supposed to be a big high eigenvalue. So the bottom can't be above the top, right? Therefore, we get that mu bottom is equal to negative mu top. Okay, so this then tells us some possibilities for what we can have with our ladder of eigenvalues. Let's think about the possibilities. Okay, we need to say that the bottom is the negative of the top. Okay. We also need to say that the spacing between the steps on the ladder is h bar. Right? That's what we figured out way back yesterday, when we found, the eigenvalues are something and something plus h bar, something plus 2h bar, right? So the spacing between things has to be h bar, and the bottom has to be negative of the top. Okay, so what are the possibilities, right? Well, one possibility is we could just have two steps like this, okay? We could have a step at plus 1/2 h bar and minus 1/2 h bar. And that's it, okay? That would be one perfectly reasonable answer. Okay? Or we could have a ladder with 3 steps. And then the steps would be at 0, h bar, negative h bar. Or we could have a ladder with 4 steps. And there could be, let's see, it would be 1/2 h bar, 3/2 h bar, negative 1/2 h bar, negative 3/2 h bar, or 5 steps, right? And then it's 0 h bar, 2 h bar, negative h bar, negative 2 h bar. What about a ladder of 1? I guess that would work too. Okay, we could have just 1 step on the ladder, and it's just a step of 0. Right? So that means in all these possibilities right here, mu top equals 1/2 h bar. Mu top equals h bar. Mu top equals 3/2 h bar. Mu top equals 2 h bar, or way over here, mu top equals 0. Okay, so it's not a single solution, but there's a family of possible solutions. Okay, we can have a family of states with 1 or 2 or 3 or 4 or 5, right? Any positive integer number of states. We can describe this, right? And the way that people describe this is, the factor of h bar everywhere is a little bit annoying, okay? So let's just say the allowed values of mu are m h bar, where m is an integer or a half integer. Okay, and then let's say m goes from negative L to positive L in steps of 1. And we'll say where L is an integer or a half integer. So instead of characterizing each of these ladders by what's mu top, people normally would characterize them by what's the number L. Right? So this is L equals 0. Here's L equals a half. L equals 1. L equals 3 halves. L equals 2. Okay, so we get different families, different ladders, depending on what's the L number, okay, which can be an integer or a half integer. And that's actually how the ladder over here was labeled, right? So over here, you can actually see the little L that the textbook authors put there. Okay, so the top here is at L h bar, and the bottom, I don't know what they wrote, but this is negative L h bar on the bottom. Okay, still good? Okay. Now, we can also use this method to find out what is the eigenvalue of L squared. Okay. We can do that because we know mu top and mu bottom in terms of L. Okay. So we know mu top is equal to L h bar, and mu bottom is equal to negative L h bar. But we have already a couple of equations for lambda in terms of mu top and mu bottom. Okay, so we had, for example, lambda is mu top times mu top plus h bar. Okay, so this is L h bar times L h bar plus h bar. Okay, So if we factor out the h bar squared times L times L plus 1. And the whole thing better work also if I do the same calculation with the bottom. Ha ha ha. Let's see if it works. Mu bottom times mu bottom minus h bar. So that's negative LH bar times negative LH bar minus h bar. Okay, and the minus signs cancel and it's still the same thing. H bar squared times L plus 1. Okay, so to summarize, we have states characterized by two quantum numbers. Quantum numbers, which are L and M. Okay. And then, we don't know what the eigenfunctions are, but we can just label them, okay? So we could say, let's call them some function f subscript L superscript M. Whatever they are, that's a name for them. Okay. And then we know L squared acting on the state is equal to lambda times that state. So that's h bar squared L plus 1 times that state, FLM. And likewise, LZ acting on the state is h bar M times FLM. Okay, so this is what we have found so far. Okay, and so all of this is for L equals 0, 1, 1/2, 1, 3/2, etc., integer or half integer. And M is minus L plus 1 up to L minus 1 up to L. Okay, so these are the eigenvalue relationships. Okay, and you know, I've devoted now an hour of trying to figure these things out. Okay, but we've got them. So what can we do with them, right? Once we have them. Okay? Well, for sure we can make expectation values. Okay, so let's see about expectation values. In the state F sub L super M. Well, the expectation value of L squared. Right? So that means this combination, right? The inner product of FLM with L squared with FLM. Right? So that is FLM acting on h bar squared L plus 1 acting on FLM. So this is h bar squared L plus 1 times this inner product of the state with itself, which should be normalized. All right, so this is just H bar L plus 1. So that's an expectation value of LZ. Okay, no, not LZ, L squared. The same thing for the expectation value of LZ. This is H bar times M. What about for LZ squared? Well, there's, for LZ squared, we apply LZ twice in one of these expectation values. All right, so that's H bar squared, M squared. These things mean that the uncertainty in LZ is LZ squared minus the average of LZ quantity squared is 0, right? That this state has a definite value of LZ. Okay, what about the LX and LY? Well, we know the state doesn't have a definite value of LX and LY. It can't because there's the generalized uncertainty principle between LX and LZ, or LY and LZ. We can talk about the expectation value of LX squared plus LY squared. Right? This is the same thing as the expectation value of L squared minus LZ squared. So the expectation of L squared minus the expectation of LZ squared. So this is H bar squared L plus 1 minus H bar squared M squared. The important thing to notice about this expression is that it's always positive. It's never 0. Right, so for example, if M is equal to L, then this expectation value, L x squared plus LY squared, right? This is H bar squared L plus 1 minus H bar squared L squared. Let's see, the L squareds cancel, but there's still an H bar L there. All right, so it's positive. The way people visualize it is with this figure over on the right side of the screen. The idea in this figure is that this is a plot of LX, LY, and LZ. Okay, and so here we have the states for a particular example, L equals 2. So here, in these states, we have different possible values of M, which means different possible values of the Z component of angular momentum. Right? So here, there are the M equals 0. Here, M equals 1, M equals 2, M equals minus 1, M equals minus 2. Okay. So the notion is that in each of these levels, there's a range of possible states in terms of Lx and Ly. Right? That states is not the right word, but possible observable values of Lx and Ly. Right? That if we have the m equals 0 state, for example, then we have this whole circle of possibilities. This circle of possibilities indicates that there's a definite value of Lz, right? The whole circle is at Lz equals 0, right? Nowhere else. But the circle encompasses a range of possible observable values of Lx and Ly, right? That Lz has to be 0, but Lx and Ly can be anything around this circle. Likewise, if you're in the state m equals 1, then Lz is equal to h bar. For sure, definitely. There's no other possible value of Lz. But Lx and Ly could be anything around this circle. Okay, so there's this whole set of possibilities. I should emphasize, I'm just talking about points on the circle, not the interior, not all of this interior of the circle, but just the edge of the circle, right? These are all possible values of Lx and Ly that go along with Lz equals h bar and L squared equals h bar squared times 2 times 3, right? So 6 h bar squared. And likewise, here's the m equals 2. It's a smaller set of values for Lx and Ly because Lz is bigger, right? So that's why this circle is getting smaller, because Lz is bigger, so there's less available for Lx and Ly. Okay? And similarly down there in those possibilities with negative Lz. Okay, so that's the story about the eigenvalues. Okay, so we set out to find the possible eigenvalues of L squared and one of the individual L's, Lz. And so we've got it, right? So the eigenvalues of L squared are h bar squared times L plus 1. And the eigenvalues of Lz are h bar times m. Now, what about the eigenfunctions, right? So here, I haven't told you the eigenfunctions yet. I just gave them labels, right? So let's call them f sub L superscript m. Okay, so what are the eigenfunctions? Well, the answer to this question depends on whether L is an integer or a half integer, right? I told you that those things are both possible. If L is an integer, okay, then the eigenfunctions are what we have already found. They are the spherical harmonics. Y sub L super m of theta and phi, right? These are functions that I already told you about, and I told you they'd be useful in different places. So here's another place where they turn out to be useful, right? So that the function FLM, you know, our real notation for that is YLM of theta, and phi. You know, these things already have the right kinds of quantum numbers, right? Where L is an integer greater than or equal to 0, and M is an integer from minus L to L. Okay. And so this is something that, I already told you about. Now we can see maybe the reason why people chose the letter L for one of those quantum numbers is L is for angular momentum. Maybe that's why they use it. I don't know. But it makes sense. It's an angular momentum quantum number. Right? Now, maybe you're thinking, do I really believe that? Do I believe that these things are eigenfunctions of L squared and LZ? I want proof. Let's try it out for some examples. Okay, so I'll switch to Mathematica here. So if I stop that one and I share, here's some Mathematica. Okay, so here's some Mathematica code for thinking about angular momentum. Okay, so first I'm going to define all the right operators. Okay, so I'll start with the linear momentum. Okay, so for linear momentum, I have operators px, py, and pz, which just calculate negative I h bar times the derivative with respect to x of the function, or the derivative with respect to y, or the derivative with respect to z. Okay. And then what, right? Well, then I can say if I want the Lx the Lx operator, that is y times pz acting on any old function minus z times py acting on that function. Okay. And likewise, if I have Ly, that is z times px minus x times pz, acting on the function. All right. And the Lz is going to be x times py minus y times px, acting on the function. Okay, and what about L squared, right? Well, that is Lx squared plus Ly squared plus Lz squared, okay? And when it comes to operators, you remember Lx squared means you let Lx operate on the function twice, okay? So here's a function, I put it into Lx, and then the output of that, I put it into Lx again. That's Lx squared acting on the function. Likewise, here's a function, I put it into Ly, and then I put it into Ly again. Right? And here's the function, I put it into Lz, I put it into Lz again. Then I add up those three things. Okay, so this is the L squared operator. Okay, now let's choose a spherical harmonic. Okay, how about if we start with the 0, 0 spherical harmonic? Okay, so that spherical harmonic is just a constant. What do I get if I work with this constant? Okay, if I work with this constant, then, well, if I want to take all the derivatives with respect to x, y, and z, I should really convert it from theta and phi to Cartesian coordinates. But this is a stupid example because it's a constant. We do something not a constant. How about L equals 1, M equals 0? Okay, that's something that's in spherical coordinates, okay? So I should really convert that into Cartesian coordinates. Okay. I will do that with this code right here. I take the spherical harmonic and I substitute in what is theta and what is phi, right? To do the conversion from spherical to Cartesian, assuming X, Y, and Z are real, of course. Okay, so if I do that, then my function turns into this whole thing in terms of Z divided by the square root of X squared plus Y squared plus Z squared. Okay, so now this is a nice thing that I can act on with my operators. Okay, so if I let LZ act on it and divide it by the function itself, that's 0. Okay, that's what it was supposed to be, right? Because it's an M equals 0 state. Right? What about if I let L squared act on it and divide by the function itself? Then I get, it's a constant, and the constant is 2 times h bar squared. Is 2 correct? Well, it's supposed to be L times L plus 1. All right, so that's 1 times 1 plus 1. Right? 1 times 2, that's 2. Okay, so indeed, this state is an eigenstate of LZ and L squared with the eigenvalues that it's supposed to have. Okay, what about if I put in L equals 1, M equals 1? Okay, here's the spherical harmonic in spherical coordinates. Here is the spherical harmonic in Cartesian coordinates. Okay, if I let LZ act on it, that's just h bar times the function. Okay, that's good, right? M equals 1, that's what it's supposed to be. Right? If I let L squared act on it, it's still 2h bar squared times the function. Okay, let's go up higher. How about L equals 2, M equals 1? Okay, here's a function, the spherical harmonic in spherical coordinates. Here's the spherical harmonic in Cartesian coordinates. The LZ acting on it, yep, it still goes with M equals 1. L squared acting on it. Now it's 6 h bar squared. 6, because that's 2 times 2 plus 1. Okay, well, so this is proof by examples, right? I don't know, I'll try another one. How about L equals 4, M equals 3? Here, just to make one up. Here is the spherical harmonic in spherical coordinates. Here is the spherical harmonic in Cartesian coordinates. Is this still going to work? Let's see. The LZ eigenvalue is 3h bar. The L squared eigenvalue is 20h bar, okay, because that's 4 times 5. All right, that checks out, okay. What about if I did Lx instead of Lz? Let's just try it and see. Lx acting on that. Okay, you can see this is not a constant times the function, right? Lx acting on the function is not a constant times the function, right? Likewise, Ly acting on the function is not a constant times the function, right? So this thing is not an eigenfunction of Lx or Ly. It is an eigenfunction of Lz, but not Lx and Ly. So it's an eigenfunction of Lz and L squared. Okay? So that's my proof by examples that that the spherical harmonics are in fact the right eigenvalues of angular momentum, L squared and Lz, when L is an integer. Okay. Clear on that? So far, so good? All right. Now, what if L is half integer, right? That's this other set of possibilities that we haven't covered yet. Okay, that is an interesting and tricky kind of situation. Okay, so what we have done so far, right, is we were working with the algebraic relations, right? That is the commutators of angular momentum. Okay. So based on those general principles, we found that we can have L to be an integer or a half integer. Nothing else, not a third of an integer, right? But integer or half integer. Okay. Now, we have a good interpretation of how to interpret the integer states, right? The integer states correspond to different eigenfunctions for an electron that's moving around. Okay, the spherical harmonics, could describe an electron that's moving around. And so now we know in each of those states, what's the angular momentum of the electron that's moving around, okay? So for example, we have the solutions for the hydrogen atom, right? And so the solutions for the hydrogen atom, right? Each of those special states has a certain energy. Now we know each of those states also has a certain angular momentum. Each of those states also has a certain L squared and a certain Lz. Good. Well, what about the half integers, right? We have now found that there is no function of theta and phi which corresponds to the half integer solutions. Well, I haven't proved that for you, but I'm telling you, there is no function of theta and phi that corresponds to the half integer solutions, okay? So that means that there's no way that the half integer solutions can be associated with the position of an electron or any other particle. But that doesn't mean that they're totally unphysical. It just means that they're not associated with the position. They might be associated with something else associated with the particle. Okay, that's not position. The point is that particles might have other kinds of properties besides their position or momentum, how they're moving, okay? So let's look at an example of a particle here, okay? So here's my particle, the baseball, okay? And the baseball is at a certain X, Y, and Z, okay? So it's at a certain R, theta, and phi, right? Because you can change back and forth between X, Y, and Z, R, theta, phi. Right? But that doesn't tell us everything about the baseball, okay? Because the baseball might also have some internal state. For example, the baseball might be spinning. Okay. If the baseball is spinning, that doesn't change its r, theta, and phi, right? That the x, y, and z, or r, theta, and phi, those things have to do with where is the baseball located. The spinning is not related to that. The spinning is a different property of the baseball. The spinning is some kind of internal state of the baseball. But it still has angular momentum, right? Spinning is another kind of angular momentum. So then we could say, how could we put the spin of the baseball into the theory? Could that be another property that goes into the theory somehow? And maybe that will go along with the half integer angular momentum states. So that's what I want to do next, right? To think about how spin of a particle can be an extra property. Okay, so let me sort of briefly get started with that now, and then I'll continue on Thursday. Okay, so to begin thinking about spin, let's see, the iPad here. Here it comes, good. Okay, so I want to start thinking about spin. So the point is that for an electron or any elementary particle, there could be two kinds of angular momentum. Okay. And typically, people refer to these things as orbital angular momentum and spin. Okay. And these things work in classical mechanics, right? For example, if the Earth goes around the sun, right, the Earth has some orbital angular momentum moving around the sun, and the Earth also spins on its axis, right? It does both of those things, right? And so those are two kinds of angular momentum which add up. And the orbital angular momentum is associated with the position of the Earth and how the position of the Earth is changing, in particular, the position of the center of the Earth and how that is changing. Okay? And then the spin is not associated with motion of the center of the Earth. The spin is just the Earth changing its internal state. Okay. This works in classical mechanics, and we know what's going on in classical mechanics. We know that when the Earth is spinning, really, we could look at every little bit of the Earth, every bit of dirt in the Earth's crust, and we could say, well, the spin really means that every bit of dirt is moving about the axis. When it comes to an elementary particle, we don't really know what is spinning, right? If we say that an electron is spinning, it's not clear that the electron has pieces that are moving. I don't think there's any theory in particle physics where the electron has pieces that are moving, right? But even without having any pieces, turns out it's still a part of the quantum mechanical description of nature to say that the particle is spinning, right? And so, here we call it spin. It's not really clear what is spinning. But still, let's just say it is some internal state of the particle. Okay, so particles have some internal state. We don't know what they are. We don't know how to visualize them really, but we do know that they're there. Okay, and so we can represent it by an operator, because that works for everything in quantum mechanics. Okay, so we'll say, let's represent spin by the operator S. Okay. We don't know how to visualize it, but even though we don't know how to visualize it, we still know a lot about how to work with it, because it should follow all the same rules for a Hermitian operator. So this is one of the reasons why the textbook goes through all of the mathematics in chapter 3 about how to work with operators just as mathematical objects. It's because sometimes we don't really have a way to visualize stuff. We just have to follow the rules for the right kind of mathematical objects. Okay, and so I'm going to say there's a spin operator, and we could say it goes along with an SX operator and an SY operator and an SZ operator. And I don't really know what these things mean in terms of visualizing parts of the electron, but even so, I can follow a lot of rules for calculating stuff. Okay? And this actually leads to a lot of what people have achieved in quantum mechanics. Okay? So we can follow the rules for a Hermitian operator. And then we can also say, all right, because spin is a kind of angular momentum, it should have the same operator algebra as L. It should have, let's see, the same operator algebra, that is to say, commutation relations as L, right? That we derive general commutation relations for L just because it's a kind of angular momentum. So that should work for spin too. So we should be able to say, whatever spin is, I don't know what it is, but whatever it is, it should be like L in the sense that the commutator of Sx and Sy should be IH bar Sz and so forth. Sy Sz should be IH bar Sx, and Sz with Sx should be IH bar Sy. Okay, so anything that we prove based on commutators should work for spin, same as it works for L. So that's going to be the basis for our discussion of spin. Okay, and that I'm going to have to postpone till Thursday because I'm out of time now. Okay, so on that note, I will stop for here, and I can answer questions about any of this stuff if you like, and then I will see you guys on Thursday. Okay.